So as I warned you, I'm on the bad laptop. I think I figured out what happened with the microphone. I think I've solved that problem, but the bandwidth problem may still be there. So if I get laggy, or if you can't hear me, or if my video disappears, can you please let me know? Okay, I'm not doing it on purpose, I promise. Technical difficulties are never intended. So let me see, housekeeping stuff, as I mentioned just a minute ago, but for the people online, I updated grades this morning. You should be able to look at your homework 3. Not everyone has finished it, so we can't go over it as a class, but I can happy to answer individual questions about that. The next homework that you have is not going to be due until the end of finals week, so you get a bit of a break for that. The very next thing you have to do is a formative assessment, so that is available right now. You should be able to answer the first 3 questions right now, and the 4th is what we're going to be talking about this week. 2 points for giving it an honest try, as usual. A couple questions from folks. As a reminder, I do accept late work. So if you can't get to something by the deadline, you get a 2-point deduction for homework that's late, a 1-point deduction for a formative assessment that's late, but you still get your points if you can manage to get it done at some point. So it's not 2 points per day or anything like that. After formative assessment, then we have our first presentation starting on Tuesday of next week. Just 1 on Tuesday, and then there will be 3 per day after that. I had posted the rubric as to what I'm looking for. I am going to be not posting your videos for the presentation recordings to YouTube freely available. They are going to be locked down to some extent. I think what I'm going to do is build an unlisted YouTube playlist and send out the link. So that way you can still access them easily, but they won't be searchable, they won't be public. I don't see the need for that. So for those of you who are on the YouTube who are not in this class, playing along with us, we're going to go dark for the next few weeks, but never fear, the last week of classes, I'm planning to be back in action to talk about group designs, I think. So clustered, longitudinal, or when people change groups over time, a little bit of coverage on that. So we'll see how far we get this week. We'll find out. I've got a lecture, I've got an example. I doubt we'll have time to go over anything else other than this, but I plan on building a list of resources for the things that I wanted to get to and wasn't going to get to in terms of intensive longitudinal data, including location scale models as the one topic that I didn't get. But I know of stuff. I can send you links to videos and papers and things like that, so you'll have some resources available. So I think those are the announcements. Am I forgetting anything? Don't think so? Okay. All right then. So we have a new unit then to start with. Lecture 5 is what I have open. I also have open example 5A. 5B does not exist yet. I'm waiting to see if I have time to build it and or present it. Let me start the screen share. We'll see how we're doing. It's loading, it says. Come on, you can do it. You can do it. Come on, you can do it. It still says loading. Oh, it's green. All right, can you see my yellow slides? Excellent. Yes. Thank you. All right, we're ready to talk then. Let me make sure the recorder is still participating. It looks like it is. It says it's overloaded, but I think that just means that it's on a delay, so we'll see how this goes. All right, so we're getting to time-varying predictors in the context of within-person change. So everything that you already know is still relevant. We're just going to add to it in terms of complexity. So first, a little bit of review, and then the new stuff follows here. So still talking about, for a time-varying predictor, 3 different types of slopes that you can examine with respect to how it relates to a time-varying outcome. In the purple there, do you have a within-person relationship? So the idea of more than usual or within-person fluctuation and predictor, is it associated with time-specific differences in the outcome? So this was a common point of error on your last homework. If I'm talking about like well-being, for instance, at that occasion, that's a within-person relationship, as opposed to well-being across the study, which would be a between-person relationship. So up to this point, the within-person relationships that we've seen are only concurrent, but we'll also look at a few models that have lagged relationships instead, because that's a very common thing that people want to be able to do. So within persons, The idea is if you are higher on X than usual, are you higher or lower on Y than usual at that same occasion? So a level 1 specific relationship. If so, that would explain residual variance. In the green, level 2, between person. So if I am higher than other people on X than average, then am I higher on Y than other people on average? And if so, that would capture random intercept variance of the outcome. The contextual effect is the weird one. That's also a level 2 effect, and it refers to between person differences, but it's after controlling for the within person variable. So after controlling for whether or not I had a stressor today, or after controlling for my level of negative affect today, what is the overall incremental contribution of my person mean in the level 2 model? So within plus contextual equals between minus within is contextual. You can get back and forth as long as we're only talking about fixed effects. Okay. Remember, does this sound familiar? Good so far? All right, moving on then. So 3 choices that you have in terms of how you can specify your model to make sure that separate level 1 and level 2 slopes can be obtained. The first one is within a univariate MLM framework. So the idea of using, say, R-Elmer, StataMix, SASMix, those kinds of programs where you're predicting one column in your data set at a time. That's what I mean by univariate, multi-level. You can do person mean centering, or what is known more generally as variable centering. And the idea is that you are manually carving up your level 1 variable into its within part and its between part as 2 separate observed variables. So this is a brute force partitioning rather than a model partitioning, so that you have variance at each level captured by its own predictor. The reason I like this is because you always know what you're going to get back. The level 1 variable only has within person information, so it can only carry a within person relationship. The level 2 variable only has between person mean differences, therefore it can only have a between relationship. Good and good. Your other choice, still within the univariate framework, grand mean centering or constant centering, because which constant you pick doesn't really matter. Then you're not carving up the level 1 variable, but you are controlling for its within person versus between person different effects by adding in the person mean. So then the person mean carries the contextual effect after you put it in. If you don't put it in, then you run the risk of having a smushed effect instead, where you're assuming between and within slopes are the same. The one that we've seen just a little bit starting last week was within multivariate multi-level modeling. So this would be within a multi-level SEM type of framework or just a single level SEM framework, latent centering. And this just means, hey, can you take my time varying predictor and pretend like it's an outcome? Cool. And so then rather than having a person mean as an observed variable at level 2, you have an estimated random intercept. Rather than having a within person deviation as an observed variable at level 1, you have a residual at level 1, the same as the outcome. So there's a parallel structure in how we treat X and Y. Then you can have covariances between them at each level, directed slopes between them at each level, whatever you feel like having. And this is the one where you have to pay attention very carefully as to whether you end up with contextual effects or between effects, because it varies as a function of model specification. And we'll have more about that in the example that follows. So this is all where we've been thus far. Graphically then, the idea of person mean centering would look like this, where we take our original X predictor and we manually carve it up into these observed boxes, but they parallel what is happening on the Y side. So random intercept is to person mean, as level 1 residual is to within person deviation. They're trying to do the same thing, they're just doing it in different ways. On the Y side, we're letting the model do the carving up. On the X side, we do it ourselves. Contextual effects and constant centering looks like this, where we don't carve up the level 1 variable, but we do add its person mean in to fill in the gap to get to what the full between effect would be when you add within and its contextual effect together. If you want to have random slopes, though, don't do it that way. So if you want to have a random slope for your within person variable, meaning individual differences in the within person effect, between person differences and the effect of the level 1 predictor, another way to say it, then you have to make sure that the level 1 predictor only contains within level variance. You can do that via person mean centering or via latent centering, but leaving the constant centered version in would be a mistake because that leads to a smushed random effect, and it's very difficult to add in the corresponding random contextual effect. Right, Vladimir? He's working on this as his master's thesis, believe it or not. We like a challenge. I have only seen one data set so far where I got the random interrobang to estimate. I've only seen it made it work once, so we're going to see how often that actually happens. But the take-home message is if you're doing random slopes, just use the version of the model where the level 1 predictor only has within variance, either via latent centering or person mean centering. Okay, so back to this then, variable centering. This would be the analog for observed variables, and then if we switch out the boxes for circles, that's latent centering instead. So then we have a directly parallel structure via a multivariate analysis. All right, so that was the review section. Now on to new stuff, but before I do that, any questions or comments? Or things I can say again? Back to the 7-Up today.
I have a quick question.
Sure.
In that slide, I can see that your level 1 within person residual variance, that's one oval. So that's the same thing when we assume that for the different residuals over time, those will be constrained to the same number.
The variance
Numbers,
is,
for example.
yes, the residual variance
The variance.
is the same number, yes.
Okay, so is that the same idea than using the R metrics, this idea of the same variance over time and no covariances in this analysis?
Yes.
Is that similar?
Yes.
Okay.
Yeah. So theoretically, it depends on your software, how you're approaching it, whether separate residual variances per occasion are a possibility. If you're doing it in a long format, so multi-level SEM, then you just have a within model. You don't have a separate potential variance for each occasion. I don't even know how I would try to do that, at least within M+. I'd have to do it via some other custom like Stan or something to where you can write out whatever you want. If you're doing it in single level wide SEM, where each occasion is a separate box, and therefore each box can have a separate residual variance, then it's a choice whether those variances are the same number, you put the constraint in to make them all be the same, or whether you let one or more of them be different. My preference is to start with them all the same. That way the intercepts and slopes for change over time would capture any variance heterogeneity and any covariance heterogeneity. I want them to have it up on the top of the model. But sometimes, even after introducing that, the residual variances want to be different across occasions or one or more of them. And I think it's okay to let it do that so long as you don't run into convergence problems. Where it's going to be more of a problem if you have fewer occasions. So like if you only have 3 occasions, having 3 separate residual variances plus a random slope is a just identified model or very close to it. If you had 10 occasions, having 10 separate residual variances is probably overkill. Maybe 1 or 2 of them might want to be different, but not 10. So.
Thank you, Lisa.
Sure. Other questions? Okay. So everything I've said up to this point is predicated on a really important and testable assumption that the time-varying predictor only contains between person mean differences, and that's why it only takes one circle to capture its level 2 dependency. That all we have are person mean differences via a random intercept or a person mean box, and that's all we need to fully separate out what is between person level 2 information from what is within person level 1 information. So that's what the rest of this is about, is what happens if that's not the case. So if you have a time-varying predictor in a longitudinal study that contains systematic change over time, so the time-varying predictor itself grows or declines over time, that's what I'm talking about. If you only have fixed change, so there is an average trajectory through it with no individual differences, then you can still use person mean centering or any of the 3 strategies, because after you put in a predictor for time or time squared or whatever it needs to be in the fixed effects, then the within person box, the slope for it is going to be controlled for the effect of time. So it's the unique effect after controlling for time. That way we don't have to worry about it. So that is fine if you have fixed change only. But if the time varying predictor itself contains random change, individual differences in decline or growth over time, that's where the problem comes in. Because then thinking about between versus within is too simplistic. Between what is the question? Between person mean differences, random intercept, between person differences in change, random time slope, and possibly more than one type of time slope if you have nonlinear change or piecewise change or something like that. So in this situation, we can't do person mean centering anymore. There's two different kinds of between person variance. That means the person mean is an incomplete representation of all the ways people differ from each other. It also means that what you would think of as the person mean is conditional on one occasion only. So here are two examples from my book. This is chapter 9 that we're in right now. I would recommend reading it. I wrote it to describe these things, and I wrote it for folks who are trying to teach themselves, so hopefully you have an advantage hearing it from me as well. But the picture on the left here is designed to convey differences in trajectories for a time-varying predictor when it doesn't show change. So in this case, capturing between-person intercept differences as mean differences only is fine, because people don't change rank orders over time if they have parallel trajectories. Even if these trajectories had a slope to them, so long as it's the same slope, the trajectories are parallel, and all you need to know is the mean difference across time, and you can characterize differences between people. But what about the picture on the right here? If I captured my intercept at the mean here, say at age 15, I'm going to have a different view of how people differ from each other and who's relatively higher or lower than if I captured it via an intercept at 12 or an intercept at 18. People change around. So person mean differences is not specific enough. Mean differences when is what you need to know, because who is high and who is low changes over time if people are on different trajectories. So the intercept itself is potentially misleading, besides the fact that we're missing this other way that people differ from each other. So what we need is something that looks like this. We need a multivariate model of change where each of the variables, we're going to call it X and Y when you're thinking of one as a predictor and one as an outcome, although they're both outcomes at this point. What we need is a parallel structure where each of them can have its own between-person intercept variance, its own between-person time slope variance, so variance in change over time, and its own separate within-person residual. So at a minimum, we have two different ways that people differ from each other in X, two different ways they differ from each other in Y, and each of those can be related to each other. Likewise, after controlling for individual trajectory differences, the E's represent why are you off your line today, right? You can be higher or lower than your trajectory predicts. Well, if I'm above my trajectory on X today, am I going to be above my trajectory on Y today too? Like, do they go together over time within persons even after controlling out the systematic ways that people differ from each other via random effects? So this circle right here on the top right, I'm calling it between person change variance. So that means the time slope in the model predicting X has a random time slope to go with it in predicting X. That's what this circle means right here. The circle on the top left here is if I put a time slope in a model predicting Y, and I have a random time slope predicting Y. Those are two different things, and they can be related to each other. So I can have my X-intercept predict my my Y-intercept, my X change slope predict my Y change slope. I can have the intercept to the slope to the intercept, or whatever the hell I want. The key idea is that because I have individual differences in change, there really is no good way to represent that with a square. You can't. At the end of chapter 9, I have some examples just showing basically that if you try to output slopes and stick them in a model, it doesn't work. You don't get the right answers back, and the slopes themselves are very optimistic because they don't contain the error around them. So this is the point where if X itself contains systematic individual differences in change, it has to become an outcome so that we can distinguish between person change variance from intercept variance at level 2 and distinguish both of those from within person residual variance at level 1. That way each piece here, each pile, can have its own set of relationships to another variable y. So this is the big key concept here. Are you with me? If X changes systematically, it has to be modeled. We can't just carve it up to person mean centering, because person mean centering can't represent three things with two different variables. It's not going to work. So then what are the possible relationships? So if I think about intercept relationships, are the predicted means at wherever time 0 is related? Are the predicted rates of change related? These are between person relationships. We can also have within person relationships. So imagine two variables here that have somewhat of a noisy trajectory, but you can kind of fit a line through it to say that they're going up on average over time. But what this picture is showing is, like, for this occasion, both the black outcome and the blue outcome are above where they're supposed to be. Now they're both below, now they're both above, and so forth. So the words that people use for this are traveling together over time, or co-fluctuation, or those sorts of ideas. This is a residual relationship that's possible. And we can look at whether it happens at the same time or whether it happens at other occasions. So if I'm higher than predicted this time, does that show up in my y next time, for instance? That's what's known as a cross-lagged relationship. So those are often of interest as well. So there's three different kinds of relationships. Just to make this a little bit more concrete, a few examples. So in the world of cognitive aging, which I've mentioned many times, a common question that people like to answer is, does it all go together when it goes? It's the way people phrase it. The idea of generality of decline across both physical and cognitive domains as a function of some sort of disease process, for instance. So this is a spaghetti plot where the average trajectory is in the black line here, and these are individual people. So my question would be, like, at time 0 here, like this red person, super strong, this is grip strength. Is that same person, the same red person over here that's super smart on block design? Like, if I'm higher than everybody else on my intercept on X, am I going to be higher than everybody else on my intercept on Y? And where the intercept is based on where we've decided time 0 is. If we use time 0 as the beginning for both of these, then it's a relationship among individual differences in X at the beginning correlating with individual differences in Y at the beginning. If I switched it so that time 0 were at the end, then it would be ending differences. So, like, where did you end up? Is that rank order on X correlated with where you ended up on Y? And you can mix and match, right, Carl? So tell us a little bit about your project in terms of where time 0 is supposed to be.
You can mix and match, yeah. So for my project, I'm taking this approach, and one of my variables that does most of the conceptual work, like in terms of causing variance in the other one, I'm situating that variable with the intercept time 0 when a firm goes public.
At the beginning.
Before anything happens at the beginning.
Mm-hmm.
And then my outcome variable, that time 0 for that is going to be at the end, 5 years after the firm goes public. So it's kind of like initial versus long term.
Mm-hmm. So
in terms of the intercept relationships.
Yeah, so initial company differences, how do they relate to where the company ends up on another outcome 5 years later? And you'll get to hear all about that next week. See, this is called foreshadowing. Yeah, so you can, where you put time 0 is up to you. In particular, if you want to look at anything resembling mediation, where you're thinking of one thing as coming first and causing something else that causes something else, having time 0 be later I think gives you a stronger leg to stand on in terms of causality. It's not causal per se, but the ordering has more evidence to support it if it's different points in time. So you can move around time zero to be whatever, to make whatever statement you want to make. Beyond individual differences in intercept, though, we have individual differences in change. So, like, let me look for my colors here. Here's a blue person who's kind of fallen off the cliff after time 4. Is that the same blue person who fell off the cliff after time 4 here? So if I decline more than everyone else on one variable, am I likely to decline more than everyone else on a different variable? Do the slopes for change over time relate to each other? So all of these are between person relationships, even though the latter is a between person relationship and within person change. I'm trying to say this slowly because it's a mouthful. Time slope relationships across variables are between person differences and within person change. Are they related across X and Y? That's the idea. Question.
Yeah, so I guess I can't help but notice the on the left-hand side, our functional change plot, that's some of those trajectories are much shorter than one another, so it seems like we lost a lot of people at year 4.
Mm-hmm.
Now it's presumably we don't have that same data for the cognitive change side of the story as well. It's just not as, I guess, maybe just from the plot, it's not as obvious. But so
Yeah.
Does it matter whether you have like, I don't know, like whether the values that you have are different for these trajectories? So like if you have years of study, you have 4 years in study for functional change from 0 to 4, and then maybe you're missing 0 to 4 years in study for cognitive change, but you have after that, like how do these differences and like where the missing data is on your time metric affect like the relationship that you're going to be estimating?
Great question. I think it depends on the functional form of change. So if I just fit linear decline, then it doesn't matter if it's 0 to 4 versus 4 to 5 because the model is saying it's constant change the whole time. If I fit something else, like let's say I had a piecewise model where my pieces were 1 to 4 and 4 to 5. Well, if I don't have data from 1 to 4, then I can't really participate in a relationship with that, but I could still participate in a relationship with the second half. You'd have to, if it were quadratic change, then linear differences in change are also conditional on time 0. So you would have to keep that in mind and thinking about what that relationship captures is where is time 0 and is that the beginning or the middle or the end, and is it the same across variables? I think that theoretically if the assumptions of missing at random hold, which is what all these models assume, then it's expecting your trajectory to be accurate even though you're missing part of it. So I don't know that it's a testable thing, how that would affect it, but in terms of principles, the less data you have, the harder it is to show these relationships. And if it's something to where, like, there's a reason, like, why you didn't come back at time 5, like, that's a characteristic, like you dropped out of school or you moved to a nursing home or, like, something happened, then putting that in the model as the covariate should help to make your missing at random assumption a little more plausible. Come back. So, not a great answer, but it is a great question. In the context of aging, I've had debates with people about whether you call people who are dead having missing data or not. Because from the perspective of like regular missing data, yeah, it's not there. Like, no, it's not there. Like, there is no more data to be had. It's just unbalanced. So in that case, it becomes even weirder when you think about it's not really missing. They're no longer eligible to be part of the study, or the population rather. So how about something a little less sad? How about kids? So this is a plot of data from a study that I became involved with when I was at Penn State as a postdoc. So in the Department of Human Development is where I was. And they had a lot of family studies where they were looking at sibling and parent influences on children. And this is a study where they had recruited older girls, so from like, I want to say 14 to 19 or something, And then they later asked their younger sisters to join the study if they had any. And so they set up models to where like time 0 was age like 17. We did it at the end in the older kids, but age 15 in their younger siblings. And so then we can look at, this is individual differences in risky behavior. So this is where the example from chapter 9, that whole story was born. The idea being like, if you have an older child who's going crazy at 17, is this their younger sister? Intercept differences where the two outcomes we're talking about are multivariate observations of a family. So younger kids are the X and older kids are the Y. And is this person who suddenly got much worse over time, like, is that their younger sister who suddenly got much worse over time? So individual differences in change with respect to multivariate observations on a family, also a thing you can do. So these types of models also work really well for dyadic kinds of questions, like my actor effect on my partner's thing and my actor effect on my actor's thing and all that kind of stuff too. All right, so if you're in this situation where you're interested in the relationship between two variables or more, but 2 is the bare minimum, and each of the variables contains individual differences in change over time, then we have to distinguish that source of variance as a third thing to worry about between person differences in change. Otherwise, what ends up happening is that the relationship between the change slopes, so the change slope for X and the change slope for Y, those relationships are smushed into what would be the within person residual relationship. So it's a second type of smushing. It's a new type. Conceptually, if we look at this figure here, what I'm trying to show is what are the sources of variation that are sort of buried in an observed predictor. So if I just have my level 1 time varying predictor in my data set in one box, and it contains person intercept differences and person change slope differences, then it contains 3 things. The first step would be to do something like person mean centering. So if I do that and I make my observed level 2 predictor, I've captured the between person intercept variance at least to some extent, at least at one of the occasions, even though it would be different over time, but still within there a little bit is within person residual, because I'm using an observed variable rather than a latent variable, where the latent version would have this little part subtracted off. But what's more problematic is the bottom here. What I was calling within person more than usual also may contain individual differences in change. And so these should be 2 separate things, but they're contained in one predictor. So this is the reason why, if you have between person differences in change, whatever relationship this has to the outcome is going to be smushed with whatever relationship the within person residual has. And so this, by the way, is the same formula that you've seen in the context of why random intercept variance increases whenever you explain residual variance. This is the same reason why you get a different answer if you do latent centering versus person mean centering. Latent centering tries to isolate the random intercept variance and correct it for the expected contribution from chance that's due to the residual. So this little piece that's subtracted off, that's the distinction between person mean centering and latent centering. Here are some simulated pictures that are in chapter 9. Let me take a minute to describe how I did this here. So I made up a data set of X and Y. Each has individual differences in intercept and in change over time. And I simulated different versions of the data set that have different amounts of correlation of the 3 kinds. So in each, we could have the intercepts be correlated, either between minus 0.4, minus 0.2, 0, positive 0.2 or 0.4. We could have the time slopes be correlated to the same extent, same choices, and we can have the within person residuals be correlated either minus 0.2, 0, or plus 0.2. So what I was looking for is to see to what extent hidden relationships in observed predictors would show up as bias based on what I was expecting. So the top plot here, this is what if we used person mean centering and we had a level 2 relationship from the person mean and we had a level 1 relationship from the within person residual. And what I'm looking at here is an effect size essentially for the strength of the intercept relationship. So if there is no relationship between the intercepts, it doesn't really explain any variance. That's what's supposed to happen. If the residual relationship is in the same direction, so for instance, if I have a residual of 0.2 right here, and the intercept is 0.2, so this triangle right here, then I have more of a difference in explained variance than if they're in opposite directions. So there's a compensatory thing here where if I have the intercept relationship going one way, the residual relationship is going the other way, then the intercept relationship is too small. It's like this part is dragging it down. What's the within person residual part is dragging it down. If they're both in the same direction, then it's fine. The same thing happens on the bottom here with respect to the slope. So in this case, this is the extent of how much of the slope variance was explained by putting in the within person residual. So the level 1 effect is somehow capturing level 2 variance in the slope. The only way that can happen is because there's slope variance buried in that level 1 predictor. So it's another kind of smushing, and we see the same pattern where if the relationships are in the same direction, it's fine, but otherwise if they compete, then they bring each other, then there's a compensatory pattern. So there's a bunch of text explaining this in here, but this is sort of a proof of concept that if you don't isolate the 3 separate types of relationships, intercepts, change slopes, and residuals, then they're all kind of mushed together in ways that are predictable based on the differences in sign and amount. So the conclusion, don't do it. Fit a multivariate model where x gets to have its own change slope, have it be random, and y gets to have its own change slope, have it be random, and then you're good to go. All right, 110. We're doing okay here. I'm keeping an eye on the clock. Anything exciting happening outside yet? No, just there. Cold, crappy day in Iowa, par for the course. All right, how are we doing so far? Okay, so I think we're in the section of the slide deck that's like heading towards what not to do. I think that's where we're headed. So here is a common thing that people like to do in longitudinal modeling. They think that, well, if we're going to have effects that take time to show up, and that's a very reasonable thing, then what if we fit a model like this? I have x that was measured at some time 1, predicts my mediator that was measured at time 2, that predicts my outcome that was measured at time 3. This is a very, very common kind of analysis. But if we look at each of these boxes, what's inside them? Right, if each of these things is just a snapshot of a growth curve, then each of these boxes has at least 3 different things inside it, right? Intercept differences, change slope differences, within person residual over time. So then how do I interpret the arrows between them? These arrows are a function of 4 or more different kinds of relationships that are being commingled together because you're only taking one occasion out of a growth trajectory. So we have within person residual relationships. So it could be that if you're off your line on x in one direction, you're off your line the same way later on, like time 2 or time 3. I would label that kind of relationship as longitudinal based on the kind of information that it contains. So a long time ago when I was a postdoc, one of the people that I was fortunate to work with was Marty Slowinski, and he was at Syracuse then, and he's at Penn State now. And he used to tell me, like, if you look at a model like a path diagram or something, and you can't tell whether a relationship is between or within, ask yourself the question, could they have estimated this model if they only had longitudinal data for one person? If the answer is no, it's not within, it's between. So in this case, if I had one person and I measured them repeatedly, then I could look at whether if you're higher than usual at this occasion, are you higher than usual at another occasion, right? I can have that within person fluctuation. So I would call that longitudinal in terms of how to describe that type of relationship, even if it's at the same time, based on the idea that it only represents within person information. It's the part that you can only see by measuring someone over time. If you have multiple people, then it's possible that that within person relationship could have a random slope to it, meaning people differ in the extent to which that is the case. Number 2, intercept to intercept is another possibility for what could be driving these things. People who start out higher on one are higher at time 2 on the other, or start out higher, 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 that kind of thing. I would call this definitely cross-sectional, because the idea of being higher than someone else is critical to being able to estimate that type of relationship. We can do change slope to change slope, or intercept to change slope, or vice versa. These ones are trickier to label, because what we're talking about is the idea that each person has a change slope as a characteristic of them. So it's between person differences is the source of variation, but a change slope itself is within persons. So this is where the language of how between and within maps onto cross-sectional and longitudinal gets very tricky. Because to me, between person change to between person change is still just a between relationship, even though it's a relationship in a within person tendency. So bottom line here, if you have all 3 of these measures, these variables measured all the time, your best choice is to make use of all that information. That way you can figure out, is this path representative of intercept differences predicting each other, slope differences predicting each other, within person residuals predicting each other, or some combination? It's usually going to be some combination. But just having time x and time 2 and time 3, each of these is going to be composed of different pieces of variance, piles of variance.
Lisa, would you, if you ran this model, would you then test to see, like, graphically, if the arrow between T1x and T2m is the same as T2m and T3y?
You could answer that question, but the whole point of this is that I don't even think this makes sense to ask as a question.
Oh, okay.
That's I'm trying not to be like overly negative, but I see this and I've argued with people about it. Like, so let's say that you find a significant path here and a significant path here. What does that tell you? Because like where you got to by time 3 is a function of where you started, how much you changed, and whatever the fuck is happening at time 3 that's just like random, right? So if you have a relationship predicting where someone is, like how did they get there? Like I don't know how this is useful to know this. Unless you're, yeah, go ahead.
Oh, would an autoregressive structure help us?
Oh, I'm glad you asked. That's coming up. Maybe it could. Yeah, maybe it could. Let's see here. Yeah, I've got, that's number 3. It is coming up. I don't think we're going to get there today. But to foreshadow, let me go back to the picture again, to foreshadow here. So let's say that I have time 1x predicting time 2x predicting time 3x, and I do the same thing for y, and then I have these cross paths. That's a very common type of model that's like 20 slides from now. Are those within, between, or something in between? That's the problem. If the variables contain individual differences in intercepts or change slopes, then it's both. It's some kind of smushed pattern. The autoregressive pattern in particular comes out of the time series literature, where before you could do anything with respect to autoregressive, moving average, or other kinds of time series parameters, you had to make sure that you had stationarity, meaning no differences in variances or covariances over time and no change. So in time series literature, what they would do is like literally try to detrend the data, fit intercepts or slopes, and then compute the residuals from that, and then do the time series analysis on the residuals. Nowadays, we don't have to do that as separate pieces. We can do it all in the same model, but the same concerns that the time series people were worried about still apply. Because autoregressive paths can be a complete artifact of unmodeled differences in change. I have a paper under review right now talking about this, and maybe if it gets published, you can read it someday.
Well, because I was wondering, if you're using structured residuals, Maybe I'm completely off this. Isn't there something kind of paradoxical about trying to model based on stuff that we don't know at all, like unknown variants? Does that make sense?
Not quite. So structured residuals is the answer to how you can have the autoregressive and cross-lag types of things, but they are in the model along with the intercept and slope factors that distinguish the sources of between-person relation. The structured residuals thing, which is, I'm going to talk about that, is a way to ensure a separation of the within-person variability from the between. Otherwise, it becomes a different model where they all feed into each other, and that is called an accumulating model, and they're a bit of a nightmare to figure out what they mean.
That makes more sense.
Yeah, I don't like the accumulating models at all. So, okay. Other thoughts, questions?
So,
Yes?
in the case, for example, if we have a quadratic effect of time with a random slope in our X predictor, in that case, we would need two new terms to represent those two sources of variance, right?
Yep.
Okay, and so on.
Yep, and then my list just got longer because then I could have my quadratic slope predict my quadratic slope as another reason why these two things are related over time. Yep, it just keeps getting more complicated. Yep.
Thank you.
Thank you. All right. Okay, so when would you do this? Multivariate change, the idea of modeling intercept differences, change slope differences, residual differences, and then all the relationships across variables. One is to fully disaggregate between and within person variance, so prevent this smushing problem that we've been talking about. Another is to salvage a curve of factors model that falls apart. So this is example 5b that doesn't exist yet, but I hope I can make it soon. We can turn it around and do factor of curves instead. Number 3 is what the question was just about, autoregressive and cross-lagged effects to do it properly. So whether my last times x predicts my current y and vice versa. In order to answer that question, which is a within-person question, we have to fully distinguish the between sources of variance first. And then the big enchilada, longitudinal mediation. So if you think about mediation pathways through all of these different sources of variance, some of them are between, some of them are potentially within. You can have slope-to-slope mediation or intercept to slope or intercept to slope to intercept, however you want to think about it. Between versus within is the key idea for all of these things, though. All right. So for those of you who are in project land, oh wait, that's all of you right now. Many of you are in project land where you're dealing with these sorts of multivariate change models. So I put together just a couple slides to help you with that process. The very first thing that you should be doing is staring at each variable individually as an outcome and figuring out what kind of fixed and random effects you need for change for it. So even if you're going to end up with a model with 6 different variables in it, do one at a time. So we want to be able to figure out what an unconditional model for change looks like per variable, regardless of whether you're thinking of that variable as a predictor or an outcome. So long as it has individual differences in change, it has to be modeled as an outcome. Unconditional model of change means what fixed time slopes do you need? What random time slopes do you need? Is it linear? Is it nonlinear? Is it linear? Is it piecewise? What is it? Do you need any extra stuff? How to go through this process, though, depends on which type of estimation framework you're working in. So first things first, saturated means. You can do this regardless. Treat time as a categorical predictor. So if you're in a wide format single SEM, you can estimate a separate intercept for each variable and only have a random intercept variance without a mean. Then you can just see what the means are. In that case, you can get a sense as to what type of trajectory it is. If you are in long format SEM, you would have to make a series of dummy codes for mean differences. So if I had 5 occasions, I would need 4 contrasts to differentiate each occasion from a reference occasion and then put the means back together again. It's a bit more work, but you can get to the same place. If you have unbalanced time, you can temporarily round it so that you can get some means to make a picture with. That way we can try to figure out what type of trajectory we're trying to model on average. If it's possible to do so, trying to figure out the answer key for the variance side would be unstructured variances and covariances. That's only going to be possible in univariate, multi-level, or wide data SEM. It is not a thing in multi-level SEM. It's also not a thing if you don't have balanced occasions. Any type of variance that changes over time points to the need for random time slopes in addition to random intercepts. Then we can consider the residual variances. Do they need to be the same over time or do they not? That's only a choice, again, in wide data or univariate MLM. That's not a thing in multi-level SEM. And residual covariances, same as that. It's a thing in univariate MLM or wide data SEM. It is not a thing in multi-level SEM. You can potentially have paths instead of covariances, but only after figuring out what the time slopes and intercepts part should be. So all the things that we did in the first class, that's step one. Figure out for each variable in your story what kind of fixed and random stuff it needs in it for change over time. Question.
Yeah, this is a question about the project, but I think other people will be thinking it's useful as well. So if you go through this whole process for understanding your individual time varying variables, in my case it's like firm lawsuits and firm performance, right? But it could be any two time varying variables.
Yep.
And you figure out it needs random time slopes, random linear time slopes, random quadratic time slopes, and autoregressive, error struct, like you got
everything.
And then you go to try to, do it in your multi-level structural equation model, and you can only capture a small part of that big picture. As you know, this is the situation that I'm in.
Mm-hmm.
What do you say in terms of knowing that these time varying predictors or time varying outcomes have things about them that your fancy model, which technically partitions the variance correctly, can't, you just can't get it to converge. What do you say at that point? I guess I'm asking you to present for me.
Oh, I seriously, no, you're not the only one that I've answered this question for. I put everything together and it blew up. Now what? That's basically the question. Well, if Jonathan were here, he'd be like, this needs to be Bayesian analysis and Stan. That's what you should do. You should spend 3 years programming it to make it converge. He's not wrong. But I would also think about what is the least wrong alternative compromise that you can make, right? Okay, I told you, if you can't have linear and quadratic, is latent basis can we work with that as a reasonable substitute? Because we don't know what the right answer is in real data ever, but we can come up with something maybe that's a little simpler but still plausible. In terms of, well, I can't get it to work, so I'm just going to do person mean centering and put this back in Elmer. That's more wrong than a compromise of latent basis over quadratic. This type of thing also goes the other way, by the way. So Nathan, I'm going to use you as an example because he was trying to fit a model with 8 or 10 different variables, and he gave them all random slopes to start with, but not all of them needed random slopes. So his model didn't converge because he was trying to estimate things that the data didn't want. And that's a different problem. And so in his case, he needed to simplify and only fit random intercepts for the variables that didn't have any change over time, and then things will go a little bit better. So yeah, this is, when you look at the articles that are describing these models and any of the dynamic SEM stuff or the residual SEM stuff, it's not a coincidence that they have 2 variables in their analysis because that's probably all they could make go. And it's also not a coincidence, I think, that the same example data sets show up in these papers over and over and over again because they found a situation in which they could make it go, and they're going to stick with that example and use it in all the papers. So the challenge is real, and I don't always have the right answer. But I think trying to figure out what would be least wrong as a compromise is the strategy.
All right, that's going to be a title to one of my PowerPoints.
That's fair. That's fair. This is the least wrong solution, and also to be upfront about it as a limitation. I mean, there would be a footnote, in your results section, preliminary analyses suggested a quadratic model. However, the quadratic wouldn't converge, so we did a latent basis instead or something. Like, be upfront. That's, I think it's, saying we tried to make it work and it wouldn't work, is at least honest. Maybe during the review process, someone will have a better idea as to how you could have made it work. And I don't think it's as just, well, just do it in Bayes. It will always work, because you're running Bayesian models right now and they don't always work. So,
Yes, exactly.
yeah, it's the complexity is real. The complexity is real, folks. So, I'm trying to give like guiding principles, but I'm also a pragmatic kind of person. All right. Other questions, thoughts? Yeah, go ahead. Yeah, Nathan wants a rebuttal.
Well, no, this is all true. Although I do have to do a rebuttal against Stan, because it's, Stan is wonderful. But I stand. But so for our projects, because I'm getting to the point where I'm starting to bang my head against the wall with some of these things. If we get like where the model is giving realistic answers, but some of them are insignificant, or maybe the global model fit is just slightly not good. Is that something you can present, or is that like a no-no?
Present in class or publish?
Present in class.
Oh, you can always present in class.
Okay.
As long as you've like, if something is breaking, I don't want your slide to be like, it didn't work, the end, I'm done with my presentation. Like, the next 7 slides should be, here's what I tried to do instead, and here's what happened. If you can't ever get a good fitting model, that's not going to be held against you. That just may not be possible with your data. So, like, what I'm looking for is that you know what to look for. Like, that you've learned enough to be able to go through the process and do reasonable things, and that you've also learned enough to know when you need help and to ask for it. I don't expect us to know everything or do everything perfectly. This is a work in progress.
Okay, that makes me feel a lot better.
And I am going to be learning Stan, by the way. This summer I am co-teaching a workshop with Jonathan, and he proposed it all in Stan, and I'm like, you realize I'm just going to be relegated to being your TA, right? Because I don't know any of this stuff yet, and I'm going to have to learn it and then present it 10 minutes later. So I'll check back in with you at the end of the summer, and you can ask me if I'm a Stan or not. I suspect I know the answer, though.
The patience needs to be endless. That's my recommendation.
Yep. All right, folks. Other questions on this topic or otherwise? Yeah, slide 2 is then try to put everything together. Once you figure out what each variable needs univariately, if your predictor has random change variance, it needs to be an outcome. That's the bottom line. So, like, if you do this in your presentation and you're like, well, I used person mean centering, and I'm like, does your variable have change? Yeah, it had change, but I did person mean centering anyway. So this is like a guiding principle. Person mean centering does not have a place for change variance in it. It's going to be buried in the within person predictor, and therefore the relationship between the change slopes and other things is buried within the within person relationship as well. If your time varying predictor does not have change in it, then person mean centering is a reasonable alternative. So at that stage, then, when everything is together, how the variables relate to each other is up to you. You could have covariances among your intercept and slopes. You could have directed relationships where one predicts the other. The one thing I would keep in mind, though, is that if I have a relationship of something to a change slope, that something should probably predict the corresponding intercept as well. So if I have a predictor X and I'm interested in predicting the intercept, that's like saying X has a main effect. If I have my same predictor X predict the change slope for that variable, then that's like predictor by time interaction. So it would be weird to me to fit predictor by time without having the corresponding predictor main effect as a relationship with the intercept. So I'm not sure if it's wrong per se, but from everything we know about linear models, that would not be done if you did it in like an Elmer kind of way. So the same principles that you've learned, I think, apply in these cases as well. And then the challenge is try to figure out what's contextual and what is between. So, but I got to go pick up my kid before the tornadoes get him. So this will be all for now. Any questions before we call it a day? All right, then stay safe this afternoon. Stay informed. Keep the Twitter on or the radio on or wherever you get your weather information. And hopefully, I will see everybody on Thursday in person or on Zoom. Your choice. All right. Thank you, folks. Have a good one.